And we're recording.
Hello, everybody. I'm Oliver Pergams. I'm a professor at City Colleges of Chicago, professor of biology, and also at the University of Illinois at Chicago. And this is my colleague and co-author.
Hi, I'm Charmaine. I am a professor at Purdue University Northwest and have the pleasure of teaching both psychology courses at both the Westville and the Hammond campus. And today we're going to spend a little bit of time talking about our research on reading aloud in college science class. We can go to the next slide.
Mm-hmm.
So let's start with the question. What do students hate to do the most? In our experience, the answer is probably the same that it is in your experience. And that's reading their textbook. The next slide includes some reasons that students don't like reading their textbooks. As a matter of fact, they'll do almost anything to avoid reading their textbooks. Oliver, if you could advance to the next slide. Although we don't really know why this is, there are some common speculations. One of them is reduced attention span. Another is poor preparation and earlier education. If reading skills and an emphasis on reading have not been enhanced through K-12 experiences, then reading in college classes might be a little bit of a challenge. Of course, there is the possibility of laziness. And finally, the difficulty with managing and understanding scientific jargon, particularly in STEM courses. These challenges, along with the specific challenge of reading comprehension, make it really difficult and uncomfortable for some students to read. So what do? They simply avoid it. Oliver?
So mostly because of this, in fact, that students hate reading, and especially hate reading textbooks. And it's amazing. They'll do just about anything rather than read, even if it takes longer than actually reading. But so I decided to use a free text, an OER text, developed by Rice University, funded by different foundations. And this was Concepts of Biology, an OpenStax book. It was free. It was, the quality was pretty good, but it made absolutely no attempt to reduce scientific jargon, no attempt to simplify language, and it was pretty dense. So, you know, the free came at a certain price. So most books wouldn't have been much better. Also, I got tired of being the sage on the stage. I got tired of, you know, lecturing in front of the class, using PowerPoint. And I wasn't, you know, really thrilled with its effectiveness either. To be honest, for this book, this Concepts of Biology book from OpenStax, when I first began to use it, there weren't any slide presentations, so you know, I couldn't use those anyway. And Charmaine.
So based on this, we had to come up with a solution. What can we do besides the sage on the stage? And one option is what we call read aloud, think aloud. Before we get into what that is and how it works, I want to talk a little bit about the theoretical basis for it. Specifically looking at learning theories and the research of Lev Vygotsky, a Russian social psychologist, we thought that the developmental theory of Vygotsky would apply here, specifically two important concepts. One is the zone of proximal development, and the other is scaffolding. As you can see in the illustration here, the zone of proximal development is what I like to call the sweet spot, right between the things a person can do on their own and the things that they can't do at all. We have this spot shown in yellow here where they can accomplish something, learn something, do something with the support and the assistance of a more knowledgeable individual, whether that be an educator or whether that be, in some cases, even a more knowledgeable peer. Then the support that's provided to help the learner move through the zone of proximal development is referred to as scaffolding. Scaffolding involves giving assistance and guidance as the learner develops skills. Places we might see this happening, obviously, is in the classroom when a teacher is assisting and directing their students, but you can also see these interactions between peers. So in K-12 education, we see this, for example, in multi-grade classrooms where older children help the younger children to learn skills. But even in the community college setting, this can apply. Most of us who teach or have taught in the community college setting are very aware that we have a diverse student population and their level of knowledge, skills, and understanding varies quite a bit as well. So they can even provide some support and scaffolding to one another. However, in our research, we focused on the educator or the professor in the course being the primary source of scaffolding to move the learner from what they can do to what they can't do by moving through the zone of proximal development. So let's look more at about how that works.
Go ahead.
Next slide, please.
Mm-hmm.
The next slide, please.
This is the next one.
So what are the goals of scaffolding in science education? As I'm supporting my students, what is it I'm trying to accomplish? Well, three main things. First of all, content understanding. As I was thinking about examples here, I thought about my statistics for the social sciences class that I enjoy teaching. And it's a content area that many students are uncomfortable with. So of course, we really want them to learn the various statistical skills. For example, understanding the mathematical concepts and the research methodology behind a paired t-test. But not only do we want them to understand the concepts, we want them to be able to utilize those concepts. And so the second goal of scaffolding in science education is procedural skills. So in this particular example, that would be how to calculate that paired t-test, whether doing it manually or using software such as SPSS. And then finally, metacognition. Metacognition is knowledge of and understanding of how you think, how you process, how you learn information. And this is important to the learner so that as they run up on challenges and difficulties, they can figure out how to navigate their way around them, learning the material. So these are the three important goals of scaffolding in science education: content understanding, procedural skills, and enhancing metacognition. So let's look at the next slide that will address how we do these things. So we've got three key elements of scaffolding here. First of all, as I mentioned, Vygotsky was not only a developmental psychologist, but a social psychologist. So it's important that social interaction is a part of scaffolding. Connecting with and relating to the learners is very important. In our classroom interactions, we might start our day by talking a little bit about how we've been doing or asking the students how they've been doing. It may seem irrelevant, but what it does is it builds that sense of community and connectedness that we then utilize to encourage learning in the read aloud, think aloud approach or other forms of scaffolding. Visual representations are very important. We might use videos, we might use drawings or writing on the board, we might use physical models in many cases to encourage and support learning. And then finally, we've got written or spoken prompts. The written prompts are obviously the instructions for some assignment or task that students are encouraged to do. But spoken prompts are really important as well. And these often require us as educators to think on our feet. So for example, when I teach neuroscience and I am talking about the structure of a neuron, one of the assignments that we do is to have them build a neuron using whatever possessions they have in their bag or their purse. And so they build a model of the neuron and they explain to me how it works. Obviously, this allows us to create a physical representation. But what I'm doing is I'm milling around the room, and watching them do this is given spoken prompts, right? I'll notice that somebody listening to the conversations and watching them build the models, I'll notice they don't quite understand a concept. And so I'll take a minute to encourage them to think about that concept differently, or explain to them how I think about that concept so they get a better understanding of the function and structure of the neuron. So that's the use of visual representations and spoken prompts along with social interactions to encourage learning. And we'll see how these are all used in reading aloud and thinking aloud as well. Oliver?
So using this research from this educational psychology research and using my own experiences in the classroom, I decided that we try something different. I thought that we would, instead of lecturing, we would read the textbook chapter by chapter, paragraph by paragraph, taking turns. And my thinking was that this would force the students to actually read the text. Why? Because I see them reading it in front of me. In structure, it would be similar to a study group, with my role being essentially a high-powered or expert study group leader. I would be included among the people reading, so I would take my turn reading a paragraph or two. And my job as this expert study group leader was to elaborate upon the readings whenever there was an actual question by a student, or whenever I thought the material needed explaining based on visual prompts, as Charmaine alluded to. And I would use videos or props or texts or ancillary writings, anything I could to elaborate and explain the concepts. And the idea was we don't go on until everybody understands everything. Charmaine, please.
So once we developed this approach to reading aloud and thinking aloud in the classroom, 3 classes were involved in the application of this approach, which we later then tabulated the data and included in the paper that we're discussing today. We had a Biology 122 course taught in the fall of 2015, which included 8 students. Environmental Biology, Biology 119, in the spring of 2016, which included 14 students, and Biology 122, taught in the fall of 2016, which included 12 students. So this gave us a total of 34 participants between the 3 classes. And as you'll see, these small numbers are important as we move forward. We tried using these techniques with larger classes, such as the Biology 114 for non-majors. This class had 32 students as opposed to the 8 to 14 in the majors class. And what we found was that this was really too much. Because as you're going around the circle, taking your turn to read, you have to stay engaged, you have to pay attention to the previous reader, and then you come back in when it's your turn. And if you have 32 people, it just takes too long for your turn to come back around. And people's attention spans just are not there and they get distracted. And we're more likely to lose their focus and attention. So based on this in the biology classes Oliver talked about, as well as a couple of courses I tried at Purdue, we found that if we keep the classes to less than 15, this method is appropriate, but for larger classes, it really doesn't work. Of course, it's also important to get students to buy into new techniques and ideas in the classroom. So at the beginning of each class, the concept was explained to students, and not surprisingly, we ran into 2 types of objections from students. One, the perception that reading out loud in the classroom is baby stuff, right? Not surprisingly, because even when we looked at the literature and the research out there about reading out loud, much of it was in the K-12 environment and probably more specifically third grade and lower. And then also this argument that reading aloud is not my learning style. There are different approaches to learning that seem to fit different learners better. And although some of the more recent research has suggested that learning styles are not as important in learning as some have previously suggested, students pretty much still buy into the concept of that. And so if it doesn't feel like a good fit for them, they don't want to do it, understand. That said, the idea of trying this was put to a vote, and all three classes agreed to give it a couple of weeks and see what happened. And after 2 weeks, they voted to continue.
Yeah, they voted to continue for the rest of the semester. At this point, I think we'd like to try it with the people here. We'd like to give a demonstration, and I hope you guys are willing to participate. So what I'm going to do, I'm going to put up a scientific paper that's, kind of heavy on jargon. It has to do with evolution, and we're going to take turns reading the first page or two, and I'm going to try to do the same kind of thing I do in the classroom to give you a good demonstration. So the first thing I'd like to do is ask all of you to buy into this. I like you to promise that for any word or any concept, anything that you don't understand, that you let me know, and then we'll take care of it. We'll make sure that you do understand it. That's the only promise you have to make. Everybody unmute themselves for a second. All 5 of us. Yeah. And repeat after me. I promise to ask questions.
I promise to ask questions
About anything I don't understand.
About anything I don't understand.
Thank you very much. So I'm going to put up the paper. And I think I better I have to do a different share, right, Charmaine? Do you see the paper, or do I need to reshare?
Yeah, we don't see it.
Okay, got it. Now you do, right?
Yep.
Okay, so this paper, rapid morphological change in black rats, Rattus rattus, after an island introduction. I think we're going to jump right into it. We're not going to do the authors are myself and 3 students from Olive Harvey. We spent a year just the 4 of us, we spent a year researching and writing this paper, which was kind of a luxury. And I'm going to jump to the text, and I'm going to read the first one, and then I'm going to ask for questions. Okay. So, rapid evolution involves changes that occur over less than 100 years, though discussion in terms of generations is more useful. And let's think about that. Let's think about that for a second. I think that I noticed a couple of faces that were a little bit questioning. Let me tell you first, let's talk about evolution for a second. My definition of evolution or natural selection, the main mechanism of evolution, is living long enough to have babies. It's a very simple definition, and it works for a long time as you study evolution. The better an organism is adapted to an environment, the more likely it is to survive and have babies. Now, traditionally, evolution rates were measured over years. So, for example, if a mouse's tail grew X amount of centimeters over X amount of years, that would be the rate of tail growth. But another way to measure evolution is over generations. With that evens out differences in lifespans. So, for example, a a human generation equals maybe 25 years, but a mouse generation is about 4 months. So we have, in the time that there's one human generation, there's 75 times, there's 75 mouse generations. This is really important because the only time evolution occurs is when the traits get passed on to babies. So while in 25 years, humans have 1 chance at evolution, mice have 75 chances. And obviously, we can see evolution, if we don't adjust for time, if we don't adjust for generation length, we're not comparing apples and apples. So that was something I wanted to talk about. Please, are there any questions now in this paragraph? We're just talking about the stuff we've done so far here, the highlighted. Are there any questions, any other questions on that? Going once, going twice. Okay, so let's have a volunteer, please, to read the next paragraph.
First, oh, go ahead, Deja.
Okay. Some of the first recognized examples of microevolution came from studies of island rodents. An increase in body size is often documented and usually attributed to release of mainland selective pressures. In a study of tricolored squirrels in Malaysia, Indonesia, and Thailand shows an inverse correlation of body size with island area up to about 100 kilometers, above which body size increases, shows that trends in body size associated with islands were tied to the animal's absolute size. Larger mammals tend to become smaller on islands, and smaller mammals tend to become larger.
Okay, first let me ask, what questions are there? And remember, you guys promised to ask questions about what a word means or what a concept is, so anything like that. Please go ahead and ask.
What is mainland selective pressure?
Thank you. And we did not plant this, by the way. The selective pressure means things that cause natural selection or evolution to happen. For example, a mouse on the mainland, say a mouse in California. Mice on the mainland are going to be likely smaller than mice on an island for the following reason. When you're on the mainland, there's a lot of different species and there's a lot of predators, like cats. And you have a selective advantage of being small gets you not caught. In other words, you can hide better if you're small. So when there's a lot of predators around, it's likely that the animals are smaller than they would be if there aren't a lot of predators around. Now, if you release this selective pressure of predators, in other words, if you bring these mice to an island where there aren't any predators, like this is the one we're talking about here, there's no reason, they don't get killed if they're big. Whereas on the mainland, they basically got eaten, and if they were too big, because they couldn't hide well, on the island, they doesn't matter. Then nobody's going to eat them no matter how big they get. And that's what we refer to as a release in selective pressure, predators versus no predators. This particular thing we're talking about now, this particular thing is the mice and the rats evolving in relation to each other, and that's called coevolution. And we'll talk about that in a little bit. So, any other questions, please?
What's the role of food availability versus predators and body size, and mainland versus an island?
Appreciate that. That was what I was alluding to just now. That well, part of it. The bodies, well, not with island size. So you're right. So the following holds true. There's an inverse correlation of body size with island area. In other words, as the island gets bigger, it's likely that the animals on it become smaller, like mice. The small animals become smaller and the big animals become bigger. And previous research has shown this to be more or less true. There were later research that showed that there's a limit to this, that once islands get to a certain size, it doesn't affect how big animals are anymore. The other interesting thing is that big animals get smaller on islands. So these same islands we're talking about today, these channel islands, they had mammoths come over long ago, and those mammoths ended up evolving to much smaller size because there weren't really the resources and the food. So in that case, the little ones were the ones that survived because they didn't need as much food. You have pygmy mammoths that you can dig up on the island that are only 4 feet tall, which is pretty amazing. Did that answer your question, or?
Yeah.
Okay. Any other questions, please? I think I covered what I thought you might need. So how about the next volunteer for comparing?
I can read that.
Okay, thank you.
Comparing cranial and skeletal traits as well as body size, Pergrams and Ashley perform a meta-analysis of rapid morphological change in island rodents. In Mus musculus after introduction to islands of the North Atlantic, in Rattus rattus after introduction to the Galapagos Islands, and in Paramyscus maniculatus on the California Channel Islands. The authors confirm that microevolution of both gross body size and cranial and skeletal traits are greater on smaller and more remote islands.
So first, what questions do you have? Are there any words you're unfamiliar with besides the scientific names? Okay.
I don't have any.
Okay. You're pretty good on those. Yeah, I think there isn't really too much there. You understand all the concepts okay as well, everybody?
Yeah.
Yeah.
Thank you for answering. Okay, how about we try the next one? Oh, another volunteer, and we only have that many people, so if you want to go a second time, we appreciate that too.
The 8 California Channel Islands, including Anacapa Island, are each home to an endemic subspecies of deer mouse, Paramyscus maniculatus. The land vertebrate fauna of the Channel Islands is diparterate, and deer mice are the only land mammal species endemic to all 8 islands. Deer mouse populations reach high densities on several of the islands, probably because there are few predators and seem to exhibit cyclicity in population size, as do voles and lemmings.
Yeah, so I'd like to illustrate some things now. And let's move over to a new share. Let's see. Now let's put ourselves where. Can you guys see a map in front of you? Okay.
Yes.
Okay. So these are the California Channel Islands. Let's make it a little bit bigger. Okay, so here's the California Channel Islands. These 5, 1, 2, 3, 4, and 5 comprise Channel Islands National Park, which is off the coast of California. Here's Ventura, California, and down below here is San Diego. And these 3 tiny little, you can't see it here, I'll show you on the next slide, that they are together, they form Anacapa Island. Now, this is a picture of Anacapa Island going from east to west. So this is the first of the little islands called East Anacapa, Middle Anacapa, and West Anacapa. And then here's our protagonist, one of our protagonists. This is the mouse we're talking about. It's the Anacapa Island deer mouse, Paramyscus maniculatus anacapae. They are big, because of the no predators that we talked about, and they are very dense populations here for the same reason. If you late summer, if you walk around the island, you are pretty much certain to kick one or two out of the way, just if you walk through the brush, there are that many. And here's our culprit, the black rat or roof rat, Rattus rattus. And here this rat is eating a bird, a bird egg, a shorebird egg. Now, the National Park Service wanted these rats eradicated, number one, because they ate these bird eggs, and number two, because they preyed on the mice that were native to the island and belonged there. Now, this picture here shows how those rats got on the island in the first place. But those rats are not endemic. Those rats did not evolve there. They came from the mainland in some way or another. And apparently they came through this ship, the Winfield Scott, in 1853. It ran aground, this ship, and the rats jumped ship and they went on to Anacapa Island. And the last picture I wanted to show you was this population size cyclicity that paragraph talked about. And this is kind of rare. So this line here represents the population size of the mice on Anacapa Island over time. And it's really odd. Most charts like this are logistic charts. They have like an S-shaped curve. This one has just a sine wave. What happened? Well, here's what happens here. There are no predators on Anacapa of the mice. Until the rats got there, there weren't any predators. With the rats, there are some. With no predators, that means the mice population can grow and grow and grow and grow and grow. And as it grows, they eat up all the plants. So there's no predators keeping the mice population in check. Then, with all the plants eaten, the mice starve. And then to make it even snowball a little bit more, as you may know, when female mammals, when their BMI becomes too low for too long a period of time, in other words, when they don't have enough body fat, they become sterile, either temporarily or permanently, depending upon the situation. So here we had a situation where not only were the plants gone, but because the mice were starving, the ones that did live were going sterile on top of it. So the population plummeted and gave the chance, though, the plants had a chance to grow back during this time, and they did. And the whole population started going again. The whole cycle. No predators, population surge, eat all the plants, mice starve, female mice go sterile, population plummets. And the period between one top and two tops is about 2.5 years. So every 2.5 years, this cycle occurs. Are there any questions on these figures I just showed you, please?
No.
Okay. And and then we're going to, did we do that one? Let's see. Wrong way. Okay, I think are we on the last paragraph? Let's see. Two more. And can we have a volunteer for this paragraph, please? The endemic mice. Endemic means native. It means you evolved there. Volunteer, please.
I'll read it.
Oh, thank you.
The endemic mice on Anacapa Island were found to have mostly become smaller, including in body size between 1940 and 1978, except their noses became broader and their ears became larger. These trends are not matched in the other two California Channel Islands evaluated, Santa Barbara and Santa Cruz. Also, there is no record of black rats on either island. The author suggests responses on Anacapa may be due to the presence of rats.
Any questions, please? Remember, you promised. So I have a couple of things, or small things. One of them is that those mice we talked about, and the one you saw the picture of, the ones that do belong on the island that are endemic, we discovered that between 1940 and 1978, these mice became much smaller in body size, but their noses got bigger and their ears got bigger. And this only occurred on Anacapa that we know of, and that was the place where the rats were. So we think that there's a chance that the size changes in the mice getting smaller especially, might have been due to the rats populating the island. Even the ears getting bigger would make sense, so they could hear the rats better, and smell, their noses getting bigger so they could smell the rats better. So the story works. Whether or not it's really what happened, can't be sure, but it's a decent explanation for the size of those mice changing, and that would be coevolution. The mice changing in response to the rats. And we're going to show later in this paper that the rats changed a great deal from coming on the island. And last paragraph, please. Black rats.
I can read that.
Thank you.
Black rats were likely introduced to the California Channel Islands during the mid to late 1800s, probably in 1853 with the shipwreck of the SS Winfield Scott on Middle Anacapa Islet. The ship was a sidewheel steamer that transported passengers and cargo between San Francisco, California, and Panama in the early 1850s during the California Gold Rush. Although mice on Anacapa have been evaluated for rapid change as above, rats on Anacapa have not. Our prediction is that the rats will have become larger over time due to reduced predators and release of selective pressures.
Okay, questions, please. Last chance.
I don't have any.
Okay, so this is what I referred to before a little bit. The Winfield Scott getting shipwrecked and get those rats probably getting on the island that way. And what I alluded to just now about the mice getting, the mice that already lived there, that evolved there, getting smaller, but their nose and ears got bigger. Where this paper is actually about is what happened to the rats. So we know what happened to the mice, what happened to the rats after they got on the island. And we predicted that the rats would get bigger due to reduced essentially due to reduced predators. And let's get back. Stop share. Let's see, share screen. Here. Okay. Get this out of the way. So at the end of each course, we took surveys. And the surveys just had 5 questions. They were really, really simple on a Likert scale of 1 to 5. And the questions were: number 1, reading aloud made me read the text more than I would have otherwise. Number 2, reading aloud made me understand the text more than I would have otherwise. Number 3, me acting as study group leader, elaborating on the text was useful to me. And in general, I learned how to read difficult text with greater comprehension. And lastly, I prefer a class conducted this way over a class with lecture and PowerPoints. And I asked students to fill these out when I was out of the room. It was proctored, and so we had that precaution anyway. There we go. And here's the results. And everybody seems to be guilty of having like one slide in a slideshow that they really shouldn't have put there. So this might be mine. So let's just look at the bottom here. Let's look at the total numbers. What these numbers are using simple t-tests is how likely these values are to be meaningful. And let's go through them. Reading the text more. on a 1 to 5 scale, the average was 4.15 for the 34 students, which is very, very strongly significant. Understanding the text more. For the 34 students, it was 4.09 on a scale of 1 to 5. Again, very, very significant. And then me elaborating, acting as an expert study group leader, had the highest score of all, almost perfect 5. And the last two questions, did it help me reading in general? Also very significant. The last question, I would prefer that all classes are run this way, you know, the reading aloud as opposed to lecturing. It was significant, but barely. When going into more detail, students thought that the reasons for it were they liked STEM classes taught that way, but they didn't think they liked humanities or social science classes taught that way. So they were answering kind of different for different classes in that. Taking student comments at the end of this period, nobody thought it was baby stuff anymore. You know, the people that thought it wasn't their learning style, so, you know, for example, maybe they were visual learners, they didn't change their minds, so they stuck with it. But even though the numbers are what you see, so it was a great success, actually. Oh, and it was your slide, Charmaine. Sorry about that.
No problem. So the conclusions from our research, first of all, students very strongly thought that reading aloud in biology classes helped them, as Oliver just reviewed in the data, in all of the ways that we asked about. However, they felt that reading aloud would be less valuable in other types of classes, specifically classes that were not STEM courses. So they said, yeah, it worked in biology, it might work in other STEM courses, but not in non-STEM courses. And as we noted earlier, this technique is much better in smaller classes of less than 15 students. This utilization of read aloud, think aloud is particularly helpful right now, as most of us are forced to teach in an online setting. So as we're teaching remote classes, whether you've done this before or whether this is brand new to you, one of the things that's apparent is that it's difficult to get students engaged, difficult to get students involved. It's even difficult to know if they're actually really there. Let's face it, you can log into your computer and walk away, or log into your computer and click over to Facebook or whatever it is you do. So one of the nice things about read aloud and think aloud, in addition to helping students learn the material and move them through the zone of proximal development, as we discussed earlier, is that it essentially forces engagement, right? So students have to be present, they have to be listening, they have to know when it's their turn to read, and so on. So by engaging students, the likelihood of them drifting off to sleep or clicking over to another site is greatly decreased.
Yes. Go ahead, Charmaine. You want me to?
Sure.
Okay.
Finally, we'd just like to invite you, if you are interested in trying Read Aloud, Think Aloud in any of your science courses, we'd be glad to reach out and assist you with that. You see our email addresses here given in the slides, and we'd be glad to answer any questions you have or help you arrange this for your courses either this fall or in future semesters.
So thank you. And now we have plenty of time for questions. And who's don't all raise your hands at once. Who's first? Anyone with a question, please, or a comment? Yeah.
I have a comment and a question. So when you guys did these surveys, so how many classes did you guys survey?
3.
3 classes, okay.
Yeah.
And they found that it wasn't great to apply it in other types of courses that was not out of STEM. That was out of STEM.
Yeah, right. That was kind of like a minor conclusion. So students thought, a lot of students thought this was the best way to run STEM classes and not other classes. So yeah, anyway, does that answer your question or?
Yeah, because these other I noticed, because I've been like taking notes on different presentations and discussions, and a lot of the concern is that they cannot get students engaged during online sessions. And I kind of suggested this in the less condensed version of like getting students to participate you know, in a way that they would know they're engaged, and also by like just doing the popcorn read, or I guess that's like another way to put it. So yeah, this was informative. That's why I asked like why, I wonder how they came up to that conclusion where, you know, it might not work in other like sectors of education. But yeah, this was definitely informative though.
Let
Yeah,
me say a little bit more about that though, because it's important to remember that these are student opinion surveys, right? And so this is the students saying they don't think it would be useful or helpful in other courses. You know, and our interpretation of that was maybe because they don't see those other types of courses as being as jargon heavy. That said, given that I don't teach natural sciences, I teach social sciences, I have actually used it in some of my classes, and I think students are sometimes surprised how applicable it is. So even though the responses of these particular participants suggested that they didn't think it would be useful in other classes, I've definitely seen it useful, at least from my own experience in some of the social science classes, particularly those that surprise the students with the amount of jargon or science that's present. Like when I teach the sensation and perception course, which is essentially a neuroscience course, even though it's a psychology course.
Yeah, I mean, this last slide that we touched on with all the students sleeping, you know, not only does this method work great on you know, science texts, in other words, students read them where they never read them before, and they're reading influencers in general, et cetera, all the questions we had on the survey. You know if they're there or not, and that's a pretty big thing these days. You know? I mean, I see three in front of me right now. I see Jeff Newell, Jasmine Richmond, and she just changed, and Deja Luckett. And you know, for all I know, a second ago, all three of them were over, you know, having dinner at their grandma's house or something. You know, so, but they're not. They're here, or at least Ms. Richmond is here. What other questions or comments do you have? Hey, did you say you had something, Ms. Richmond? Or? Oh, you're mute. You're mute.
Yeah, I just figured that out. But I've actually took the Bio 122 to where we actually did read out loud, and I found it helpful because some of the words I feel like it's unnecessary letters, and some of the words like they're not pronounced the way it's spelled. And some of the text does get a little confusing, even though you handpicked the text, Dr. Perkins, to where it wasn't as confusing. But the part of elaborating on how it actually affects us, the environment, the human body, it all plays a part. And I feel like that really helped because I know in most cases, people don't want to ask questions because you're afraid to be wrong. And it's like you're looked upon, like maybe you're a little bit slower than others and you'd rather just read it on your own and figure it out. But to elaborate on it made it a lot easier. Especially if you moderate, made it completely easier to remember. Because some of us are, like with me, I know I can personally, when I read, like when I get one of your tests afterwards, I can hear your voice tell me exactly that's the answer.
I'm sorry.
Yeah, I agree because now I'm in graduate school, and I took methods in inquiry, and like the text is really heavy. I studied political science, and he did the same thing. We literally sat down and we kind of read each passage, and I didn't understand what I was doing in graduate courses, but then like when I sat there and like kind of read it by myself, I'm like, ooh, okay, this is pretty hard. Like it was really easier to kind of like, and it's about 6 of us, so it was easier to do it in a smaller setting where everybody can sit and read and kind of understand the actual text and like the words in the text.
Yeah, I mean, there's nothing, as an instructor, as a professor, there's nothing like the feeling of knowing students are reading, because damn it, you're making them do it in front of you.
One of the things I thought was interesting and useful in the demonstration, and that Jasmine kind of alluded to as well, is that you, in some cases when questions weren't posed, and this happens with students, sometimes because they might be uncomfortable asking, or sometimes as you just don't know, right? So this way in which you kind of anticipated the questions or the things that might be unclear for students, and you sort of answered questions that weren't asked, I guess is the best way to say it. Explain things that people might be likely to have some challenge with. And I think that's an important part of this think aloud part of the process, right? When we focus on the read aloud piece, yes, we're reading through the chapter, but then as a educator, I'm modeling how to think about the material when I explain those concepts, even if a student doesn't necessarily have a question about them. It elucidates how to think about and understand the material for students, which helps not only with content understanding, but I think that piece we talked about earlier, metacognition, is really assisted through that process.
Following up on Charmaine, can I ask a question, please? How many of you have read whatever, something that was kind of difficult to read, and come across a word that you don't know, and then rather than look it up, you figure you're going to get it out of context later on, right? And you just skip over it.
Yeah.
Everybody's hands raised on that one, or
Yeah.
I know I do all the time with scientific articles, and this prevents that, right? If you have a much more substantive learning curve if you actually know what you're reading, and any other questions, please? Ms. Richmond, do you have any other comments? Did you find that did you find it easier to read the text? Did you find it that the questions we asked, let me go back to them actually.
The questions that you ask, like I said, like in class, I have never met any professor besides you that gets mad for not asking questions. Nobody else. And like I said, like people are afraid to ask questions and be wrong, and you get rid of that anxiety. You just elaborate on everything, and it like to read out loud. I'm gonna be honest. If you was like, hey, did you read the text and didn't make us read it out loud, I probably would have just skimmed it to do the homework. Just being honest.
Yeah. I mean, people look stuff up online. They look for other students that have done that homework already, or
well, that doesn't work for you because you change the test every semester.
Yeah, but most people don't do that. So I mean, most people just look it up online, and there's these services you know what I'm talking about. So what else we got? Deja, would you use this method if and when you're teaching yourself? Or?
Would I use it? Of course, yeah, I would actually. I wonder if like, what about like the amount of text you get? Do that also, like, I'm trying to figure out how to like pose this question.
Sure, take your time.
Like the amount of reading, is it a certain amount of reading also you get if a professor gives someone like a book to read in a couple of weeks, say for instance? That's when like a lot of scanning happens.
Yeah.
Would that fall under the same like strategy?
No, we didn't. Nobody got tested on anything that we didn't all read through.
Okay, yeah, because like I know like depending on the class, certain groups of students they have less reading versus more reading, right? And then like the point of this is to encourage students to actually like read the text other than like, you know, skimming through their text. So like what are different ways if a person have like a book to read in a week, or I don't know if you guys teach undergrad or graduate courses or post-secondary, but
So Deja, if I can jump in there and maybe try to get at what you're getting at least one of the challenges I found in trying to use this in the social sciences as opposed to the natural sciences is that our textbooks and our reading material are usually, I don't know, just longer. Perhaps we're just long-winded in the social sciences. And so we run into this challenge of how do we get people through a certain amount of reading material, whether it's a chapter in a textbook or whether it's a separate book, like you're suggesting we might instruct students to read. And this is definitely a challenge. And what I found in using it in my courses is that I had to modify it a little bit where we might not read the entirety of the chapter in the class. So what I would do was I would go through that chapter and pick certain segments that I felt like we needed to do aloud in the class because they're the ones that really needed to be explained and clarified and discussed more. So that then they may be assigned some piece of it they're supposed to do at home. And whether that actually happens or not, of course, I don't know, which is the whole point of the read aloud and think aloud in class. But it seems to be the only way to adjust it for longer or bigger reading materials is to say, let's take a piece of this, do it in class, but get the juicy pieces that we know that students really gonna need some assistance with.
Yeah, that makes a lot of sense. Yeah.
okay, yeah, that answered my question.
What else we got? Nothing? Okay, Charmaine, what can you think of? What have we missed?
I'm sorry,
I said, what have we missed, Charmaine? Can you think of anything? Or?
I think we really hit on most of the pieces here. Again, the only thing I don't want us to lose sight of is that second part, the think aloud piece. You know, we're not just reading, but we're guiding them through how to understand the material. Because if you just read, you're not getting that scaffolding, you're not getting that support and assistance in actually understanding the content. So the think aloud piece, explaining definitions of terms, using illustrations, using models, explaining how to think about this material is really important. You got to do the two pieces together in order to have an overall learning experience.
Right. You know, today I only use some photos as you know, studied as reading tools. Usually it's more than that. Usually there's videos, and when we're face to face, there's props and physical demonstrations. I didn't do the videos today in the interest of time. I didn't know, you know, how long this would go really. But that's usually part of it, and those are useful and provide interest. So I guess anything is fair game. You know, whatever you can do to help the student understand the words in front of him or her, you do. And you know, if you adhere to the idea that you don't go forward until everybody understands everything, I mean, that's the idea. That's the what I try to do. Don't have anything to add there. What other questions do we have? Okay, well, with that, I'll thank you for coming. And it was a great pleasure talking. Charmaine, do you have anything to
Not at all. Again, thank you all for coming, and I hope that something we've shared today can be helpful as you continue in your work, whether it's students, faculty, or staff.
Thank you again. And
Right,
Jeff,
thank you. Thank you.
You're very welcome. And Jeff, you can turn off the recording now.